So really the only naming you've been talking about, right, are aldehydes and ketones? That's the only new naming? Okay. Okay, so the first thing we want to be able to identify these functional groups so you know what you're actually naming. What's in both an aldehyde and a ketone?
Carboxyl group.
Close. Carbonyl group. Careful. Carboxylic acids have carbo. So C double bonded to O. We're just reviewing some like naming stuff quick, and then we can start on a specific chapter if you want. So this is our carbonyl group. How does this differ from a carboxyl group? Since you mentioned carboxyl.
Carboxyl is OCO, right?
Yeah, so it actually would have an OH.
Okay.
Okay, that's where the acid comes in. So carbonyl is just the C double bonded to the O. Carboxyl group has an OH on one side. Okay, so how do aldehydes differ from ketones?
Aldehydes are terminal. They end in
Terminal, good. So there is an H on one side. So there's an H in aldehydes. There's an H next to the carbonyl group. So ketones, if they're not terminal, they must be
internal.
Okay. In terms of naming, really the thing to remember are the specific endings for both of these. So what ending do you add in aldehydes?
AL.
AL. And in ketones? With some functional groups, we have to indicate where they are within. We have to give them a number. Do we have to do that with aldehydes?
Is that only if there's 5 or more?
No, because 4. Let's look at this. So, well, for specifically for ketones?
Mm-hmm.
Yes. For ketones, yes. For other ones, be careful. Like, for example, alcohols, it's 4, right?
Yeah.
Okay. What about with aldehydes? Do we have to use a number when...
No.
Why?
Because it's terminal.
It's always on the end. It's always going to be 1. Okay. So let's go through an example. So we know this one's a ketone because it's internal, it's not on the end. How would we name this?
So is this with the ethyl and then what's
So you're thinking of ethers.
Okay.
Ethers are COC, and we name the groups on either side.
Mm-hmm.
So with both aldehydes and ketones, you're going to follow the same process, same initial process as an alkane, okay?
Okay.
So you want to first identify the longest carbon chain. 7. Okay, so what's the prefix for 7?
Kept.
Good. Now, we know, obviously, there's a carbonyl group here. It's internal, so it's a ketone.
Mm-hmm.
So what ending do we have for ketones? So heptone. And then how would we let them know where the carbonyl group is?
Would it be 3?
3, yes. So you still want to give them the lowest number. So if we count it from this way, 1, 2, 3, 4, 5, 1, 2, 3. So keeping the lowest number, 3 heptone. What if Can you, oh, never mind. Did you get a chance to sign in?
I did not sign.
Okay, could you pass that paper back to her? How would the name change by adding this group here? How do we name that substituent?
Methyl.
Okay.
So it'd be 6-methyl 3-heptone.
Okay. Why not 2-methyl 5-heptone?
Because the carbonyl group gets priority.
Okay. Who knows why the carbonyl group gets priority?
Is that just the ID pack rule?
It is, but so the way the shortcut to this is by looking at how oxidized. Okay, so groups that have more electronegative groups, especially oxygen, are going to have higher priority always. So alcohols, carbonyl groups, carboxyl groups, those are always going to take precedent over methyl groups or any other type of R group. So you're absolutely right. So we have 6-methyl 3-heptone. Okay, let's take a look at an aldehyde. How would we name this aldehyde?
Propanol.
Say that again.
Propanol.
Propanol, very good. And like we discussed earlier, because aldehydes are always terminal, you never have to worry about adding a number. I know he was pretty strict about that, on some of the quizzes, not being redundant. So just be cautious of that. Amber made a good point with ketones. You would only have to put a number if it's 5 carbons or more. So let's take a look at why that is. So here we have 4 carbons. Why don't we need to put 2 propanone? Why is a number redundant here?
Wouldn't it be butanone?
Did I say propanone? I'm sorry. Yes, butanone. 4 carbons. Why wouldn't it be 1 butanone? Why is that not possible?
Because it'd be 1 on either side, right?
Well, so if we had the carbonyl group here, is this ON anymore?
No, it's no.
Okay. So for it to be a ketone, we have to have carbons on either side. And the only 2 carbons that have carbons on either side are the 2 carbons. So whenever you have butanone, the only option is 2-butanone. So when you add in that 5th or higher carbon, that's when you have more than one option and the number is required.
But would you still put the 2 for butanone?
So following his pattern from last semester, so was it propanol? Wait, no.
For which one?
The one that he, the number wasn't necessary, or I forget what it was. It was a 3-carbon one, I'm pretty sure. Or was it propanone?
It might.
I think it was propanone.
Which in that case, again, the only option for propanone is 2-propanone. That seems, I feel like it was a different one, but either way, because the only option is 2-butanone, I think if he's following that same pattern of grading, he would call that 2 redundant. This might be a good question to ask him. Like, if this was an example and you asked us to name this, would you just want butanone or would you want the 2? I've always recommended putting the number, but then he started taking points off.
He marked my question completely.
Yeah, and I know you weren't the only one, so yeah, I would just, it's a good question to ask him. But it seems like he would consider that redundant. Okay. All right. So that's pretty much naming. Again, both of these, the carbonyl group is going to take priority. So in any instance, you always want to give them the lowest number. So keep that in mind. But other than that, the process in naming is very similar to that of, say, alkenes, right? You find the longest carbon chain, change the ending based off of the functional group, and locate where the functional group is.
So with aldehydes, there's no numbering, even if there's like a substituent?
So if there's a substituent, you would number the substituent.
Okay.
But again, I believe it's like a carboxylic acid. That's always going to be terminal. So adding the 1 would be redundant.
Okay.
But for example, if we did this marker's already dying. How would this change the name?
2-methyl-propanol?
Yep. Bless you. Make sense? Okay. I'm assuming everybody wants to go over chapter 17 and 18 for the quiz tomorrow, so we can kind of run through that. I know there's a lot of reactions to keep in mind here. I'll kind of go through the reactions, but again, like I've said in the past, a pretty good baseline understanding is just to know the reactants, the products, and pretty much any intermediates. But we'll go through most, if not all, of these. Okay, so we started talking about the carbonyl group. Some of this did come up, I think, last semester, but let's kind of go through it. Okay. Is this bond polar or non-polar? Polar, okay. Which side is going to be more negative? Good. How many pi bonds are in this bond? Careful. So there's 4 bonds overall. If we were just looking at the carbon-oxygen, we have 1 sigma, 1 pi, right? If we're counting all of these 4 bonds, there's 3 sigma, 1 pi. But either way, only 1 pi bond here, okay? What would be the orbital hybridization of this carbon? sp, sp2, or sp3? sp. I heard a couple different ones. So this would be sp2. Okay. We kind of went over a kind of trick for that. Basically, you want to count the attachments. So in this case, looking at this carbon, we have 1, 2, 3 attachments. So spp, sp2. I don't know if he talked about this in class, but what's the orbital hybridization of this oxygen? One guess. Anybody else have a guess? It's a tough one, huh? The hard part about oxygen that you don't have to worry with carbon is you're always going to have 2 pairs of unpaired electrons, or unbonded electrons, sorry. And those actually count as attachments in this case. So with carbon, you typically always see their bonds. With oxygen, you have 2 kind of hidden. So these are 2 attachments. This is a 3rd attachment. So both the oxygen and the carbon in this are sp2. Okay. Technically, oxygen is now up for grabs. Okay, so you should feel comfortable with carbon. You may be asked about the orbital hybridization of oxygen. A good trick, or not necessarily trick, but carbon can be sp, sp2, or sp3. Oxygen can only be sp2 or sp3. So you don't have to worry about sp in this case. If we were looking at carbon NMR, carbon-13 NMR, would a carbonyl group be deshielded or shielded? Why deshielded?
Because the oxygen is pulling on it, so it shifted downfield.
Good. So in chapter 10 last semester, when you were talking about NMR, one of the things they say to keep in mind is the addition of electronegative groups. So anytime you have something that's electronegative, it's going to pull the electrons, deshielding the adjacent carbons or hydrogens. Okay? Bless you. So anything with a carbonyl group is going to show up deshielded in the NMR. Okay. There is a section on oxidation and reduction. This should be review from last semester, but I'll go quickly over it. This I think was actually pulled directly from a previous chapter, but when you have okay, when you oxidize a primary alcohol, what's the initial product? An aldehyde. If you oxidize it further, what do you get? This we didn't really talk about. Carboxylic acid. When you oxidize a secondary alcohol, what do you get? Ketone. Can you oxidize a ketone further? No. Good. What do you get when you oxidize a tertiary alcohol? It's actually no reaction. Now, the reason for that, if we look at a tertiary alcohol, I apologize for these markers. So here we have a tertiary alcohol. There's 3 carbon groups attached to this carbon. When we oxidize, we're adding carbon-oxygen bonds and we are removing carbon-hydrogen bonds. If we're looking at this carbon, there's no hydrogens attached here to remove. So that's why we can't oxidize this any further. If we look at a ketone that's just been oxidized, again, there's no carbon-hydrogen bond here to break. So that's why we can't oxidize that further. So if there aren't any hydrogens attached to that adjacent carbon, that's where these no reactions come in, okay? I think the reason this is brought up again, I don't know why it's really discussed last semester. So in lab, you're going to be doing a reduction. I don't know if you've already done it yet. You have?
Yeah.
So I think that's why they went through this again. But again, a lot of this is pretty much directly from a previous chapter. Okay. Any questions on oxidation reduction? Okay. So a Wittig reaction. There are kind of 2 important things that I would recommend knowing from this. So in this reaction, you make a new carbon-carbon bond. Anytime you see that, you should take note of it. It's typically in bold in these notes, so it's really easy to pick out. And this reaction uses something that's called, and I'm not 100% sure on the pronunciation of this, it's YLIDE. I call it a ylide or a ylid, but that could be an incorrect pronunciation of it. Essentially, let's see, here's a good picture of one. You don't need to know what one looks like, but you need to know that it's used in this reaction. But all a halide is something that has an overall neutral charge, but has charges within it. So for example, this phosphorus has a positive charge, this carbon has a negative charge, but overall, this is a neutral molecule, and that's all a halide is. Yes?
Do we need to know how that's made?
Did he talk about that in class?
No, but it was in the book.
Typically, I would refer to his notes on that. If he doesn't talk about it in class, he usually doesn't quiz on it. He's usually pretty fair about that. Also, to my knowledge, I don't remember that being a focus at all, so I wouldn't worry about that.
What's a heteroatom?
Heteroatom is just, is it used in this?
It's using the definition of.
So it could, basically it's phosphorus, oxygen, something other than carbon. It could also, any positive, exactly.
Okay.
Okay. The next few reactions, that you don't really have to worry about the names because the names themselves tell you what's happening. So it's not like this one where you have a reaction name that you have to memorize itself. But next few talk about different addition reactions and what's happening there. You're going to notice a lot of new functional groups. This is really the semester of functional groups. I would highly recommend, if you haven't done so already, to start compiling like basically a worksheet where you have the name of the functional group, a picture of the functional group, and any naming information. On the midterm and the final, you'll get tested on a lot of these. So I would recommend keeping track of it now. Let's see here. Okay, so let's see here. So we just talked about it. What in the carbonyl group, what charge is going, or what atom is going to have a negative charge?
Yeah.
When looking at H2O, when these break apart, which of these is going to have the negative charge? So we can kind of see what's going to happen here, right? So we have a positive charge is going to be attracted to the negative charge, negative attracted to the positive. Okay? So this is going to essentially be the pattern for all of them. So even if you forget, you can kind of visualize where these bonds are going to be made and broken. So if we have our carbon, we're going to break one of these bonds. We're going to break that pi bond. The H is going to be attracted to that oxygen. The OH is going to be attracted to the carbon. And we have two free bonds there. So this has two OH groups. What's the terminology for two OH groups? A diol. These are both attached to the same carbon. What's the terminology for that? What is it if they're on adjacent carbons? Good. Yep, vicinal. Good. Very good. So again, with addition of water, obviously you have either an aldehyde or a ketone, you're adding water to it. Really the only piece you have to memorize is the final product. You're making a geminal diol, right? The rest is kind of, is hinted at. Okay. So addition of alcohols. You're going to have two different possible products depending on what type of alcohol or not what type, how much alcohol is present, excuse me. So let's see here, we have our carbonyl group. So again, we're going to follow the same pattern here. The OH is going to be negative, positive. The R group is going to be attracted to the oxygen. OH group attracted to the carbon. So OH, R group, so carbon containing group. Okay. This is a new this in itself is a new functional group, but it's made up of functional groups you should recognize. So obviously we have an OH group, and we have this CO or COC ROC group. What is COC? Ether, right? We talked about it earlier. So you have an ether group and an OH group. When you have them coming off the same carbon, it's referred to as a hemiacetal. So this is a new functional group that you should be able to recognize. Do not worry about naming, be able to recognize it.
So hemiacetal is two functional groups, an ether and an alcohol.
Yes, on the same carbon. If we have excess alcohol, so we have a vast amount of alcohol in comparison to our carbonyl group, we get a slightly different final product. Instead of having an OH attached here, we're going to have two ether groups attached. So it's going to look like this. When you have two ether groups off of the same carbon, it's no longer a hemiacetal, it's an acetal. So hemiacetal, alcohol group, ether group, acetal, two ether groups. With these reactions, again, it's not so much, what are the reactants, because those are kind of hinted at. It's more about understanding what these final products look like and also understanding the stability of them. Does anybody remember which one of these are considered more stable?
Acetal?
It is the acetal, absolutely. So acetal is the more stable form. There's also a note here, acetals can also be used as protecting groups, which you may remember talking about that a little bit last semester. The stability is definitely the more important note to remember. Thank you, Amber. Are you feeling okay with these couple reactions? Not too bad, right? Okay. Addition of amines. Oh my goodness, what a normal marker can do. Okay. Amazing. Now, amines are a functional group you may remember from general chemistry. Anybody have an idea of what an amine looks like?
It's an NH attached to the carbon.
Say that again?
An NH, like a nitrogen.
Yes, good, yes. So essentially, I'm just gonna, you can look at it a couple different ways, but at least one of them is an R group. So you can have up to 3 different R groups. Now with these ones, it does depend on the classification, what your final product is going to be. So when we have primary amines, all that means is there's only one amine group. If we're talking about secondary, that means there's 2 R groups, okay? So when we have, I'll continue with the drawings, I think they help. So with this one, we're gonna be talking about primary. So I know this is kind of a weird way to draw it, but essentially we just have this, okay? So again, more positive, more negative, negative, positive. So you can kind of see where these bonds are being formed. There is kind of a stepwise process happening here. So the first thing that's formed is referred to as a hemiaminal. Now, thinking about hemiacetal, so hemiacetal, we're going to make a hemiaminal. You can kind of see how this might end up looking. So we've got our C. This is going to be attached to the bottom. So, hemiacetal, hemiaminal. Okay? The final product here probably one that you're not familiar with. Essentially, we're pulling water out. And that's going to drive a double bond to form between the nitrogen and the carbon. This one is referred to as an imine with an I. Okay? I would add both of these to your list of functional groups to know. Again, naming not important, but you should be able to recognize them if you're shown on an exam. Okay, if we have the same thing happening, but with a secondary. So again, this, we have two R groups on the nitrogen instead of one. I'm noticing there is a slight differentiation in the starting product here, so I'm just going to add this here. So it is going to look a little bit different, but just so we have the same kind of idea. You'll see why we have to add this, but we can see that the intermediate really hasn't changed here. Okay, we still have an OH group and a carbon-nitrogen bond. So this is still a hemiaminal. The addition of another R group doesn't change this functional group at all, bless you. So for both of these reactions, the intermediate is going to be a hemiaminal. That doesn't change. However, the final product is going to be slightly different. So the process really hasn't changed. We're still removing water, but we're pulling that H from somewhere else because there's not an H here. So we're pulling an H from this methyl group, which is going to force the double bond between those two carbons. So instead of the double bond being between the carbon and the nitrogen, we have an alkene group. This is referred to as an enamine. Ene referring to the alkene group, amine referring to the nitrogen. So we have imine, enamine. My way of remembering which type of amine goes with which, it's not a perfect analogy, but so we have primary here. The symbol for primary looks very similar to lowercase I. So when you are reacting a carbonyl group with a primary amine, your final product is an imine. With secondary, I don't have a fancy way of remembering, but enamine. I know there's a lot on the board right here. It's really just to see where these functional groups are coming from. You don't feel like you would have to complete a reaction. It's more of just knowing the final products and the intermediates here. Do you guys have, yeah, Amber?
So what's coming off of the hemiaminal? to make that unamine?
Sure. So we're still pulling off water. Okay, so we're going to pull off this OH. Let me just. And one of these hydrogens.
Okay.
That's why the double bond forms here instead of here. We don't have any hydrogens to pull off of that nitrogen. That's a good question. Any other questions about these two reactions? I know there's a lot of different terminology here that you're not used to. Are we okay to move on? Okay. Okay. Hydrogen cyanide. Some of you may be familiar with cyanide. This is another polyatomic ion that you should have been introduced to in general chemistry. Cyanide is a polyatomic ion where carbon and nitrogen are bonded together, and it has a net charge of -1. You should know that polyatomic ion. Okay, so let's take a look here. So hydrogen cyanide, we just have cyanide bonded to hydrogen. Again, it's important to remember the charge, so that way you know where that cyanide is going to want to react. If it's going to have a negative charge when this bond is broken, it's going to attack the carbon, hydrogen attacking the oxygen again. So again, we're going to end up with an OH group here. And, geez, cyanide here. This is just referred to as cyanohydrin. You will need to know that this is the final product. I don't think that this is going to be, I don't think that identifying it is as important for this one. Definitely the previous reactions, there's more focus on those, but I would definitely know the final product name for this reaction. Okay. I'm going to skip the next piece and come back to it. I'm going to talk about the last kind of 4 reactions, just since we're on this topic. Okay, so this is the last addition reaction. The next couple have names that you'll need to remember. So we've got the Wolff-Kishner. Okay. Essentially, this is just removing the oxygen from the carbonyl group. So it's called deoxygenation. But let's take a quick look at it. Okay, so we have our aldehyde or our ketone. We're adding a molecule that has 2 nitrogen groups. This is referred to as hydrazine. Our intermediate is referred to as hydrazone. I would know the intermediate. I'm sure he mentioned this reactant. I would just recommend knowing it. I don't think you have to be able to draw either of these, but you should know the process. And what's our final product? An alkane. Essentially, we've reduced the carbonyl group to its most reduced form, right? We've taken all of the carbon-oxygen bonds out of it. So it makes sense that our final product is going to be an alkane here. And I wrote reaction. It's actually Wolff-Kishner reduction, which kind of hints as to what's going on here.
Wouldn't there be see a water next to the hydrogen zone, be like that plus H2O, isn't water?
Yes. Yes. So this it's dehydrated at that point. This is not a balanced reaction. Sorry. Yeah, but you're right. Absolutely. So we'd have the oxygen and 2 hydrogens coming off of that nitrogen. Okay. So that's Wolff-Kishner. Then we have Baer-Villiger oxidation. I do want to point out in Dr. Cosper's notes, she references aldehydes or ketones, but this one, looking in through the book, I believe it's only ketones that undergo this reaction. So just something to keep in mind. So a ketone is reacted with something called I'll just write it. Peroxycarboxylic acid. You don't need to know what this looks like, but you should know that it's the catalyst in this reaction. Your final product is going to be an ester. So ketone, peroxycarboxylic acid, final product ester. The last 2 reactions that are mentioned, you actually did in general chemistry. Essentially, these are tests to see if aldehydes are present in a solution. There are 2 different types. There's Fehling's and Tollen's. I don't know if you guys happen to remember those at all. So both identify whether there's an aldehyde present. With Fehling's, you're using copper, Cu. With Tollen's, you're using silver, Bg. Essentially, you start with a blue solution that has copper 2 in it. If there's an aldehyde present, it's going to react with that copper ion, and it's going to make copper oxide, which is a very, very dark red. So we go from blue to red. In Tollen's test, you're reacting silver ion solution. This is clear, colorless, you can see right through it. If it reacts, you're going to end up with a silver participate, which it's going to look like silver. Very shiny type of precipitate.
How do we make the ornaments?
Say it again?
Is that how we make ornaments?
Yes. Yep, exactly. So with these, again, I think it's more important to understand that they identify and the type of precipitate that's left over. Those are the reactions that you should know. The last piece is just referring back to carbohydrates, because we talked about hemiacetals and acetals. Let's see. So when we're talking about carbohydrates can come in 2 different forms. They can be straight chained in a Fisher projection, or they can be in a ring structure. Okay. I'll leave off the other attachments. Essentially, we're focusing in on this functional group here. So I know it looks slightly different, but we could rearrange it to look like this. So we have a carbon attached to an OH group and attached to an oxygen that's attached to another carbon. What functional group is this? Very good, hemiacetal. Now, when we were just talking about hemiacetal and acetal, I mentioned that the hemiacetal is typically the less stable functional group there. When we're referring to carbohydrates, this can be a little bit confusing, but when we're looking at straight chain versus ring structure, the ring structure is more stable. Okay? That's not negating that previous statement because this is not an acetal. But just know that when you're talking about carbohydrates, hemiacetal is considered more stable. Okay? But that's chapter 17. Any questions on any of this? No, I threw a lot of functional groups at you.
What would be the important part to remember for that?
So, knowing that there's a hemiacetal group in ring carbohydrates, okay? But also understanding that the ring structure is more stable than the straight chain structure. Sometimes that can be confusing because we just said that hemiacetal is less stable than acetal. Mm-hmm. But this is a situation where you have the ring structure itself makes the hemiacetal more stable in this instance.
Oh.
Typically they're considered pretty unstable. Good question.
So it would be more stable than its acetal?
No. More stable than this straight chain structure, which does not have an acetal functional group. Okay. I know. It's good stuff. If you think about it, actually no, we're not going to get into that. Oh.
Yeah.
Okay. Anything else on chapter 17? Okay, let's move on to 18. How are we doing with that? Not bad. All right, this is a 4-page chapter, so there's a lot of different information here. We're going to first start out with talking about enols and enolate ions. Okay. Dr. Cosper does a good job of reminding you of some terminology here because it's really important to understand the significance of where these things are located. So when we're looking at the carbonyl group, any carbon that's directly attached is referred to as an alpha carbon. The carbon next to that is the beta carbon. That will come up again later. Any hydrogen attached to an alpha carbon is considered an alpha hydrogen. These happen to be very acidic. If something is very acidic, what does that mean about, how do I say this without giving away the answer? What does a very acidic hydrogen tend to do? Careful. It tends to fall off, which would technically deprotonate, right? So something that's very acidic, it typically disassociates, breaks off very readily, okay? If a hydrogen is connected to the carbonyl group, it's referred to as a formal hydrogen. Formal is just a common name prefix. We won't really get into that, but just so you understand that terminology.
So a formal hydrogen is attached to the
Carbonyl group, yep. Okay.
Is there anything special about it that we need to know?
Not at this time. They're not as acidic as alpha hydrogens. I would just understand what that means because he could use that terminology in a question. Okay. So, when we have molecules that are in this orientation, I'm actually going to change this. Okay, so when we look like this, there are two different forms that this can take. There's a keto form and an enol form. Okay, this is considered the keto form, which makes sense because it's keeping that carbonyl group. Some students get confused because this isn't technically a ketone, right? It's an aldehyde because it's terminal. The keto just refers to the carbonyl group. It doesn't refer to an actual ketone necessarily. So keto, carbonyl group. The enol is formed when bonds are broken and reformed so that we have a carbon-carbon double bond, an alkene, and an alcohol group, OL. When we go back and forth between these, that's called tautomerization or tautomerism. This just means that bonds are breaking and reforming in this new formation. It's important to know that this is different than resonance structures, okay? With resonance, bonds aren't actually being broken. Electrons are just moving back and forth. With keto and enol, bonds physically have to be broken and reformed. It's not a resonance structure.
And is this something that kind of just randomly occurs, or is there something?
So it happens when you are in acidic or basic environments. Okay, so it just readily will flow back and forth. And we'll talk about kind of the middle ground to this. But yeah, so anytime it's in an acidic or a basic environment, you're going to have shifting back and forth between these two forms. One last thing about these two forms, the keto form is considered more stable. Okay.
Now I talked about forms. Now, I guess I'm just a little confused. Like, that's the molecule. Trying to get my words out.
No, that's fine.
The enol form is also a. Are there any other carbons that can be associated with the keto or the enol, or that's?
So you can have as many carbons. You can have carbons on this side, or you can have additional carbons here. This can happen anytime you have a carbonyl group with an adjacent carbon.
Okay, so
Okay.
it's just the keto form of the carbonyl group. It's just the enol form of the carbonyl group.
Yes.
Okay.
All right. Okay. So enols. Now let's talk about enolate and what that means. So when you put a solution of this in, and you make it a basic condition, you're going to form enolate ions. So both of these are considered enolate ions, or enolate anions. So essentially we are deprotonating, we're pulling off a hydrogen, which leaves us with a negative charge. This is just showing that this can go back and forth. Again, there's kind of an equilibrium point, so you might have more keto at one point, you might have more enol at one point, but this is consistently moving back and forth. Okay. Because we can form two different types of ions, okay, and we have charges at two different areas, okay, we can actually attack at either of those areas and make two different types of products, right? Because we have the charges in two different areas, enolate anions are referred to as being ambident. So it reacts at two different sites, giving two different products, meaning they're ambident.
Does a keto, when a keto is, the bonds are being broken and formed into an enol.
Yep.
Is it only the right-hand side of the enolate anion, or is it possible for both? Does it form?
So if you had, are you saying like if we had another carbon here?
Well, no, like so you have the keto that's right there.
Yep.
And it's in a basic solution, so it is going to get turned into an enol.
Yep.
But it gets turned into an enolate anion first.
Yeah. Yes.
Is it specific to which one it will turn into?
Oh, I see. So are you saying, can you go directly to this?
Yeah.
So, no. Typically what would happen is you're going to remove the proton from this, but you can get electron movement here. So these are technically, you can get electron movement to shift to this. I don't believe you can go directly from this to this specific ion. I think you kind of have to follow the path.
Okay, so the keto turns into the first enol ion, which turns into the second one.
Which can then form the enol form. Exactly.
Okay.
Okay. All right, let's talk about halogenation. Everybody okay with this? All right. Okay, so when you're talking about a halogenation reaction, the final product is going to depend on whether the solution it's in is acidic or basic, okay? So in an acidic environment, we start, and this is of aldehydes and ketones. Sorry, forgot that. So, in an acidic environment, we are only going to replace one of the alpha hydrogens with a bromine. Once one is added, it kind of shuts the reaction down. Essentially, it makes it harder to form those enolate anions, okay? So what's not being shown here, we kind of is this formation here. So we're forming the enolate ion, which is going to attract the addition. So we're removing a proton, we're replacing it with a bromine. Okay? Once you make that addition of the bromine, it's harder to form this again. So it kind of shuts everything down. That's why there's only one being added. In a basic solution, we're going to replace all of them. So acidic solution, only one alpha hydrogen is replaced with a bromine or a halogen. In a basic solution, all alpha hydrogens are replaced.
With bromine?
Bromine is, it could technically be probably any of the halogens other than iodine, but the bromine is the example that was used.
What'd you say the reason for that was?
In the acidic or the basic?
In the acidic.
Okay. Once you add that initial bromine, it makes it more difficult to form an enolate ion. So you have to go through that step to make a substitution. So it's basically making it harder to make that ion.
So, enolization, is that what it was called? It makes it harder for it to enolize?
Enolize is, yeah, you could use that. Okay. We okay with this? So when we're talking about alkylation, Dr. Cosper provides kind of some things to keep in mind. We don't really talk too much about mechanisms, but there's essentially 5 points. Some of them you can kind of group together. But essentially, alkylation is considered a nucleophilic substitution. So think back to SN1, SN2, okay? So for this to run properly, we have to run an SN reaction, okay? If you use something other than a primary haloalkane, well, how do I want to put this? So typically this is an SN, which means you have to use a primary haloalkane or a halomethane. Essentially, you want to try and limit steric hindrance, right? So you don't want big, bulky, secondary, tertiary haloalkanes. If you do have something other than this, it's going to run as an elimination reaction. So anything else, so a secondary, tertiary, it's going to run E2. What's the final product of an E2 reaction? Alkene. So obviously that's not going to give us the final product that we want, okay? So for this to run smoothly, you have to use a primary haloalkane or a halomethane. Okay, so that's kind of point number one, essentially. When you're running alkylation, and we're going to talk about this reaction, but aldehydes undergo an aldol condensation. This is what you want to happen. This is a good thing. If you use a ketone, you end up with something called a multi-alkylation or polyalkylation. You may remember kind of talking about that when you were talking about like Friedel-Crafts alkylation and acylation. Multi-alkylation is not a good thing. Okay? It makes it more difficult to figure out what your final product is going to be. okay? Along with that, I don't know if I should do it, maybe let's do a picture. Okay. So when we're thinking about enolization, right, creating enolate ions, we know that we're pulling alpha hydrogens off, right? So this one is very similar. This is our example from before. So we're going to pull off alpha hydrogens from here. However, when you have a ketone, you have two sets of alpha hydrogens, which means you can get the reaction taking place here. You can have it being taken place here. Essentially, you end up with a mixture of final products. Also not good. The last piece, I don't know if he'll really test you much on. I think these are probably the more important ones. But another way to kind of prevent any of these issues from happening is to start with an enamine. You don't run into the same issues. You know what your final product's going to be. And you, again, you make enamines from aldehydes and ketones. So basically you can just add another step, and it can simplify some of this. How do you guys feel about these 2 points, though? Does that kind of make sense a little bit? Okay. So now we're going to move in and start talking about aldol condensation, okay? Because there are different variants of this reaction. This one is going to follow you probably throughout the entire semester. This is a very important topic. You're going to hear a lot about it. You're going to get really sick of it. Okay. Bless you. In terms of starting products, you're just reacting to aldehydes or ketones, okay? You can do any type of mixture of the two and it would still be considered an aldol condensation. This example is two aldehydes, but again, you could be reacting any combination of those. Okay. Essentially, this first step, you're creating a new carbon-carbon bond. Okay. I know things have kind of been moved around, but essentially, we removed a hydrogen. Wait a second. Sorry. Right. So we broke this pi bond, and we removed this hydrogen. Okay? This is referred to as an aldol. Why do you think that's its name?
So it's an aldehyde with an alcohol.
Exactly. So first step, you react to aldehydes or ketones and you form an aldol. This second piece is this a dehydration reaction. What is removed in dehydration reactions? Okay, and you can kind of see that right here very nicely. So by pulling off the OH and the H, that drives a carbon-carbon double bond, okay? This is referred to as an alpha beta unsaturated carbonyl compound. What does alpha beta unsaturated mean?
Alpha and beta carbons, and there's a double bond.
Good, exactly. So unsaturated refers to something being pulled off, creating a double bond. If we remember, the carbon directly next to the carbonyl group is an alpha carbon, and second from that is a beta carbon.
So why is the double bond formed again?
So because we pull off this OH group and this hydrogen, that's going to leave these two carbons with one less bond, so that just drives a double bond being formed. Another name for this is an enone. What was that?
A lot simpler.
A lot simpler, yes. You should know both of them. Why is this referred to as an enone?
Because there was a double bond and
Ene.
ketone.
Right. So carbonyl group, this instance, it's not necessarily ketone, it's technically an aldehyde, but just thinking that carbonyl group relates to the one, double bond relates to the ene. So this is your typical garden variety aldol condensation. Okay? There are some variants of this, but do you guys feel comfortable before I move on
What should we know, like, about?
about this?
Yeah.
Okay. So you should know starting products, intermediate, final product.
Okay.
Okay. You should know. Don't worry about like writing any of these, but you should also know we're going to talk about some of the problems you can run into with aldol condensation and how to fix those problems. So I'm going to talk a little bit about that. But definitely reactants, intermediates, final product. And then we're going to talk about some other situations. Okay. So, crossed aldol condensation. Okay. In the last part, I talked about how you can pretty much react any type of aldehyde or ketone together. The only issue with that is you run into some uncertainties. So here's a good example, and I'm going to use two different colors. So we have two aldehydes in this instance, okay, and they're reacting with each other. Now, both of these can form enolate anions, okay? Once they form enolate anions, there's really nothing dictating what's going to react with what. So we end up with a variety of products. So for example, here we reacted A with A. A with B. B with A. And B with B. So there are 4 different products of, possible just by reacting these 2 specific aldehydes together. Now, I mentioned that the reason for this is because both of these can form enolate anions. Okay, obviously we don't want multiple products. We want to definitively know what we're making. So the only way to really prevent this is by using one aldehyde or ketone that can't make enolate anions. How do we form enolate anions?
In a basic environment.
Okay, but what happens in that basic environment, molecularly?
Is it the alpha hydrogens that are?
It is the alpha hydrogens. So if we want to use something that can't form enolate ions, we want something that doesn't have any alpha hydrogens. So an example of that would be something like this. So here's our carbonyl group, here's our alpha carbon. This alpha carbon is only bonded to other carbons, no hydrogens. Okay? So this can't form enolate ions. So whatever it reacts with this is the one that's going to form the enolate ion. Okay? Because only one of these is forming that ion, the reaction is only going to take place at one location. So we're going to end up with only one product. So crossed aldol condensation is what happens when you have 2 aldehydes or ketones that can both form enolate anions. The problem with this is you end up with multiple products, not an ideal situation. The solution to this is use an aldehyde or a ketone that can't form enolate anions, in essence, something that doesn't have alpha hydrogens. How do we feel about that?
So in cross-aldol condensation, there's multiple possibilities for products, which is the problem because you don't know what you're going to get. You can't really track anything.
Exactly.
The solution is to use an aldehyde with no alpha hydrogens.
You got it.
That's the basis of it.
Yeah,
Okay.
exactly. Yep, that's the solution to the problem, for sure. Okay. The next type of aldol condensation is intramolecular. Okay. Okay, this is going to be our starting product. So whenever you have an intramolecular reaction, okay, that's compared to another reaction, the starting products for the aldol condensation have to be present on one molecule. So if we think back, an aldol condensation starts off when 2 aldehydes or ketones react with each other. So intramolecular aldol condensation, you have one molecule that has 2 aldehyde or ketone groups, 2 carbonyl groups, okay? This is an instance of 2 ketones, right? Because we've got internal, internal. In Dr. Cosper's notes, she doesn't show the ion being formed, which I think causes some, or the aldol being formed, which causes some confusion. So I'm going to add that piece just so it's a little clearer what's happening here. Okay. And I'm going to number these for my benefit. 1, 2. Do you have that drawing that I had? I just want to double check myself.
This one?
I think that's right. Yes, okay. Okay. So essentially, let me rewrite these two. Here is our aldol before it's been condensed. So this one carbon is reacting with carbon number 6. We can see that we've broken the double bond here, making an OH group. That's where that OL comes from. And we pulled off a hydrogen to form this bond. So this carbon went from 3 hydrogens to 2 hydrogens. This carbonyl group has stayed intact at carbon number 5. That hasn't been changed.
So on carbon number 1, so just kind of like bends around.
Exactly.
Okay.
Yep. So 1 bonds with 6, breaks the carbon-oxygen double bond, leaving an OH group, and a hydrogen is removed from carbon number 6. Okay? So this is our aldol being formed. Okay, in aldol condensation, once it's formed, we run dehydration. Okay, so we're going to pull off this OH group, and we're going to pull off one of these hydrogens. That's going to form water, and the leftover is going to look like this. Somebody name the functional group here. Enone. Anybody agree? Fair. Okay, I know it may not look identical to what was formed in the aldol condensation, the garden variety one, but if we look here, we have a carbonyl group, and then we have an alpha carbon and a beta carbon with a double bond. So this is an alpha-beta unsaturated carbonyl compound, otherwise known as an enone in a cyclic state.
How do you know which one? I know we already answered.
That's okay.
Which one's like alpha and which one's beta?
It's okay. So whatever is directly attached to the carbonyl group is considered an alpha.
Yeah.
So we've got an alpha carbon here, and we have an alpha carbon here.
Mm-hmm.
The carbons directly attached to alpha carbons are all beta carbons. So we have a beta carbon here, and a beta carbon here.
So why aren't like all carbonyl compounds have a beta?
They do have betas. It's just there's not always double bonds in between alpha and betas.
Okay, so it's the double bond.
Exactly.
Okay.
You're identifying where that double bond is held. This one is of particular importance because of how it reacts. Reacts in a very particular way. It's very stable. So that's why we're learning about this. But in every molecule, in every molecule that has a carbonyl group, you have alpha, beta, and actually gamma carbons. It's just, in this instance, we're looking at a very specific subset of those molecules.
So for this one, just like to show you, this would be alpha and that's beta.
Exactly.
Okay.
Yep. The next step is to talk specifically about these enones. Okay, so are you guys feeling? We finished aldol condensation. So we talked about the typical aldol condensation. We've talked about what happens in crossed aldol condensation and how to fix it, and intramolecular. So those are 3 instances that you should feel comfortable with. Okay. Are you ready to move on to talking more about enones and other reactions? Okay. So again, this is a typical enone. If we were to compare it to a different enone, which would be more stable? Meaning the one on the left? Okay. Why?
Because there's less carbon on my left side,
Okay.
and on the right structure there's more carbon, so it's kind of unbalanced.
Okay, interesting. I see where you're going with that. Instead of looking at the number of carbons, I would focus in on the distance between the carbonyl group and the carbon-carbon double bond. So remember when we were talking about dienes at the end of last semester? There's conjugated dienes and non-conjugated dienes. Enones have a very similar, are very similar to that. So we see double bond, single bond, double bond. This is considered conjugated because you have double, single, double. If you look over here, we have 2 single bonds separating our double bonds, considering non-conjugated. Now, if you think back to dienes, conjugated dienes are more stable. Same thing with our enones. Conjugated enones are more stable. Who remembers why? They're stabilized by resonance. Okay? When you have double, single, double, electron delocalization is possible. Electron movement, right? So electrons can move through those p orbitals, offering extra stability through what we call resonance, okay? Really important for this one. So enones, especially the ones that we're talking about, alpha, beta, unsaturated, are very, very stable and are more stable than non-conjugated. There are essentially 3 reactions. Addition, Michael addition, and then Robinson annihilation. With addition, there are technically 2 types. You can have a 1,2 addition or a 1,4 addition. This should also seem pretty familiar from when we talked about dienes, because we talked about essentially the same exact types. So 1,2 additions. This refers to where the additions are taking place, okay? 1,2 additions, actually let me redraw this. If we react it with something, AB, okay, A is going to be added to one atom, B is going to be added to the other. If we were to kind of number our atoms here, 1, 2, 3, 4. This is where the 1,2 comes in. So we can either number them this way or number them this way. If we number them this way, Okay, so we broke the pi bond in the carbon-carbon double bond, added something to each carbon. If we make the addition in the carbonyl group, we end up with the addition happening one on the oxygen, one on the carbon. Either way, these additions are happening on adjacent atoms, 1, 2. That's what the 1, 2 refers to. In both of these instances, only one pi bond is being broken. And you can end up with 2 different products. With 1,4 additions, both the pi bonds are going to be broken. Let's take a look at that. So again, when we're looking at 1,4, the farthest carbon and the oxygen are where the additions are going to be taking place. We break both of the double bonds. We're going to force a double bond to be formed between the 2 carbons. And we get our addition here and our addition here. So with 1, 2 additions, only one pi bond is broken, and the additions take place on adjacent atoms. In 1,4 addition, both pi bonds are broken, and the additions take place on the 1st and 4th atom.
And why is it only happening at the first carbon and not the second carbon for the double bond?
So this, sorry, are you talking about the addition here?
Mm-hmm.
So for some reason she wrote HB. I'll just do AB just for simplicity. So addition to the first carbon and addition to the oxygen.
But could you do the B on the second carbon because that's part of the double bond too?
This one?
Mm-hmm.
So that wouldn't be a 1,4 addition.
Okay.
So that would be technically a 1,3.
Would that change it?
I don't know if that's possible. I mean, most things are possible. I just don't think that would happen very readily. Essentially, because of how the double bonds are formed, again, it might be possible, but it probably wouldn't be very stable because it doesn't follow the resonance structures that would be formed. So again, if it is possible, it probably doesn't happen very readily. These happen much more commonly. How do we feel about 1, 2, and 1,4 additions? Pretty good. Okay. We just talked about a 1,4 addition. The Michael addition is an example of a 1,4 addition. I'm going to include Dr. Cosper's whole thing, but only part of it is technically this reaction. So she kind of separated them nicely, but just so you can see everything. So essentially, we're starting with an aldehyde or a ketone. Again, remembering that they can go between the ketone and enol form. When we put these in a base, what forms?
Enolate.
Enolate, very good. So this is where the Michael addition actually starts. So you form an enolate. They refer to this as a Michael acceptor. But if you look closely, you should recognize a specific functional group. An enone. Okay? So an enolate and an enone react. This is our final product. We can see 2 carbonyl groups present. So this is referred to as a dicarbonyl compound. That's technically what the final product of a Michael addition is. So enolate ion reacts with a Michael acceptor or an enone and forms a dicarbonyl compound. Nothing too crazy there. There is an additional step that's referred to as a Robinson annihilation. So I'm just going to kind of erase the beginning part here, but essentially we're going to take this final product and run another reaction. So we're going to take that dicarbonyl compound. I'm just going to redraw it just so we can see it down here. If you think back to the intermolecular aldol condensation, that's all a Robinson annihilation is. If we actually were to look back, this is almost identical to the example that they used. I don't think they had this extra methyl group, but almost identical. So thinking back, we have 2 ketone or carbonyl groups, dicarbonyl compound. This carbon 1 is going to react with carbon 6, and a ring is going to form. I did move it just a little bit, but I've just kind of spun it around. Again, almost identical to the example we used in intermolecular. There was just an extra methyl group here. But the final product is the same. It's a cyclic enone. Yes?
So the Robinson annihilation
Yes.
is exactly an intermolecular aldol condensation?
Yep.
Okay. So does it
Essentially, a Robinson annihilation is when you take this and then you do this after.
Okay.
Okay? So a Robinson annihilation is all of this. A Michael addition is just this subset.
Okay. And an intermolecular aldol condensation is just the last bit.
Exactly, of a Robinson annihilation. Not too bad, right? There's a lot of carryover from like section to section. So even though it's 4 pages, I think some of the information is repeated. So I don't think it should be too bad. Yes, Amber?
So for this part,
Yep.
what is this? Is that the enolate?
So that's just so if you were looking in Dr. Cosper's notes, that is this part. They have it enolized in this one. It's still it's the ketone. But they're just redrawing the Michael addition because that is technically part of the Robinson annihilation.
I have
Yeah.
Thank
So
you.
it's just a ketone. Like
Yes.
it's but it would be enolized.
Yes. They're just not showing that here. So basically, if the blue is the Michael edition, the red is the Robinson annulation. So this is technically the start of a Robinson annulation. It kind of pairs together two different reactions to make one. Any other questions? Any questions from the first quiz?
Can we go over the Friedel crafts?
Yep.
Calculation?
Alkylation and acylation, the two different types?
Yeah, both of them,
Sure.
if we have time.
We have 20 minutes, so we should be okay. A side note while I'm getting this up on the board, does this time work better than last semester? I don't know if you guys have heard anything from other. I know I can't make everybody happy, but I wanted to try and make it a little bit easier.
For me, because I can actually handle this one.
Okay. I know that it was a hard time for a lot of people. There it is. Okay. Okay. One thing that's going to help out with this, again, going back to functional groups. So acyl is a functional group. I don't know if it's been something that you've, talked about, but essentially, it's when you have a carbonyl group directly attached to a halogen. So that in itself is a functional group, and that can sometimes help, just remembering that can help with some of these reactions. So alkylation, you should all be comfortable with. You're adding alkyl groups. In this case, we're talking about, adding it to benzene. So I'll just draw. Okay. So, alkylation, adding alkyl groups to an benzene ring. The issue with Friedel-Crafts alkylation has to do with what happens once this alkyl group is added. Okay? This reaction is known for having polyalkylations. We talked a little bit about this in this past chapter. We talked about multiple alkylations, not knowing what your final product's going to look like. Now, this refers to the concept of orthoparameta and how those, what kind of direction that, whether that activates or deactivates the ring. So when we add an alkyl group, an R group, does that activate or deactivate the ring? It does. So R groups are considered weak activators. When I say activate the ring, what does that mean? it means it's more likely to react again. Okay? So activation gives more, essentially donates more electrons into that benzene ring and makes it want to react more. So by adding this R group, we've made it easier for other R groups to attach. So by alkylating it, by adding this alkyl group, we activate the ring and we make it more likely to activate again. Or more likely to react. This is what gives us this polyalkylation that we don't really want. So, when we're looking at acylation or acylation, we're adding an acyl group.
Is that the same as the alkylation?
Yes.
Okay. 'Cause that's what threw me off.
Oh, okay.
Yeah, that's how he names it in class.
Oh, okay.
Alkylation.
Yeah, okay. Slightly different terminology for the same thing.
But they are the same.
They are the same thing. So looking at this group here, even if you don't have it memorized, okay, is this a ortho, para, or meta director?
Meta.
Okay, how do you know that?
I just remembered that the carbonyl with the R is deactivated.
Exactly, yes. So if you, this might be in a different chapter, chapter 16, yeah. If you have an electronegative group that's not directly attached, that's the important piece. Because when you have a halogen ends up directing orthopara, either way.
So carbonyl that's not directly attached will have a meta position.
Be careful, carbonyl. So the oxygen is our electronegative group, but it's not directly attached to the ring.
So the electronegative group that's not
Yep.
directly attached.
This is considered a strong deactivator. So by attaching itself to the ring, that oxygen is actually pulling electrons out of the ring, which means it's making it harder for that benzene ring to react again. So it's preventing multiple reactions, which is a good thing. Because then we know what our final product is going to look like. We don't have to worry about additional things being added.
So it makes the final product, but then in alkylation it'll react again.
Yes.
So it'll just keep reacting.
Yeah, so imagine all of this stuff floating around, right? So we have a lot of these floating around, okay? So this benzene will kind of bump into and add this alkyl group. This alkyl group is going to add more electrons into this benzene ring, which means that when it runs into something again, it's even more likely to react.
Okay.
Whereas here, once we add this acyl group, even if it does bump into something else, this has deactivated the ring, making it less likely to react. So even if it bumps into something, it won't be added. Does that, I don't know what the question was based on. It sounded like it was just more of a confusion about the naming.
Three-part and I mixed them up.
Oh, okay.
But I guess, because the answer you had, like question number 10, was what is the functional group pulling out of the benzene ring to result in monoalkylation? And the answer was carbonyl. But it's not always a carbonyl? Is that?
So could I read it again? Sorry.
Yeah. Which one? Number 10.
Oh, what is the functional group pulling it? Okay. I see what you're saying. So if we look at chapter 16, there's a couple different options. That is one example. Did he give you?
He told the answer was carbonyl. Which is what I'm really confused on.
So I think it's because he's referring to this reaction specifically. So if we were looking at chapter 16, you see there's a bunch of examples that do have a carbonyl group, slightly different types. There are other options, which is why I said be careful.
Okay.
But because he's talking about this alkylation or acylation,
Mm-hmm.
that in itself has a carbonyl group. So he's talking about this specific reaction.
Oh, okay, so not all.
There are other types of deactivators.
Gotcha.
Yeah.
But it's specifically for the Friedel-Crafts acetylation.
Yes.
It's
This will
carbonyl.
always
Oh,
have a carbonyl group, and that will always be
Gotcha.
what's deactivating. That's a tricky one. Also, based on like reading that, I would almost say electrons, because it almost sounds like he's saying, what is the group pulling out?
Which question was that?
Question 10. But I can see where it's where it's carbonyl group, but I can, yeah, it's a little ambiguous.
It was electrons.
Oh, it was?
Yeah.
You told me it was carbonyl.
It's a bad question, but the answer was electrons.
Okay, it's a bad question.
Oh,
Using his
yeah.
words. Using his words.
He was all over the place about
Oh,
it.
so it's not carbonyl. It's electron.
Yeah, it's electrons. But
'Cause-
he gave everyone points back for that because the question didn't make any sense.
It was ambiguous, right? Because you
Yeah.
could, yeah. Or is he asking about what the functional group is, or what is the functional group doing?
Yeah.
Okay.
exactly.
Okay, so it's, oh, okay.
How are we feeling for the quiz tomorrow?
Do you still have time?
Yes. Give me 1 second.